So the title of this talk is Reuse, Don't Recycle, Transforming Lock-Free Algorithms That Throw Away Descriptors. And this is joint work with Maya Arbel-Raviv, who's a PhD student at the Technion, and I want to mention that some of this work was done while I was a grad student at the University of Toronto. So let's jump right in. Lock freedom is a progress guarantee that ensures that although individual threads may starve, the system as a whole will always continue to make progress. And as the name might suggest, you cannot use locks in a lock-free algorithm. Instead, you typically use synchronization primitives such as compare and swap, and you ensure progress using a mechanism called helping. So what's helping? Well, suppose a process P starts an operation O, and then another process Q is blocked by O, prevented from making progress. So a traditional lock-based approach would see Q just waiting for P to finish, but in a lock-free approach, Q will actually perform part or all of P's operation O on behalf of P. And the big question is, how does Q know how to perform O? I mean, P's the one who wants to perform O. How does that information get from P to Q? And one of the most common ways of communicating how to perform this operation is to use a descriptor object. So a descriptor encodes how to perform O. For instance, it might contain the arguments to O and some status information about maybe which steps have been performed already so that helpers don't redo steps and so on. And then a process that comes upon one of these descriptors will help that operation complete by invoking help on a pointer of that descriptor. This is a special function. And this help function will complete the operation that created that descriptor des. So let's look at an example of a double compare single swap primitive or DCSS primitive that can be implemented using descriptors. So here are the atomic semantics. I think by far the easiest way to understand this primitive is to think of it as just a single word cas on address 2. It's going to try to change address 2 from E2 to N2. But this single word cas has a special condition. It can only succeed if another address A1 contains its expected value E1. So let's look at an implementation of that. This implementation is due to Tim Harris, and I want to describe this implementation just giving an example. So here we have our view of memory. It's a sequence of words that each contains some value. The first step in the DCSS is to create a new descriptor and store all of the arguments to the DCSS operation in the descriptor, and we'll call des the pointer to this descriptor. Now, let me just preview what's going to happen in the rest of this algorithm by describing an analogous lock-based algorithm. So suppose that we lock A2 and then check if A1 and A2 contain the desired values. And if so, we change A2 to contain the new value and unlock it. So that would be a nice atomic solution to this problem that uses locks. Of course, we can't use locks, but we can use a sort of a lock-free lock. Instead of giving exclusive access to a process, it'll give exclusive access to the DCSS operation. So it can only be modified in accordance with the wishes of the operation. Someone can help perform the same operation, but you can't start another operation in this address. How do we implement that lock? Well, basically a descriptor pointer serves as a lock. So we basically lock A2 by trying to do a cas on A2 from E2, the expected value, to point to this descriptor des. So we're kind of simultaneously locking and checking that A2 contains the expected values. This cas will only succeed if it does contain the expected value. So here it does. We store our descriptor pointer there. Now this is locked for this operation. And note that we've replaced an application value by a pointer to a descriptor. So we need a way to distinguish between the values that are already there in main memory and these descriptor pointers. So if someone comes across a descriptor pointer, they can tell, oh, this is locked, I need to help. And so basically you steal one bit from each word in memory to distinguish. So after we've locked this address, we call help on this descriptor pointer. And this is the same thing someone else would do if they came along and saw that it was quote-unquote locked and wanted to help. So what's the help function do? We read address 1 and see if it matches the expected value, and if so, we do a cas to change A2 from this descriptor pointer to the new value. So if it contains the desired value, which it does, A1 here is address 400, the expected value is N, it does contain that, so we're going to do a cas changing from descriptor to the new value, which is D, And in doing this change, we not only change to the new value, we also simultaneously unlock. And of course, if we didn't have the expected value in A1, then we would unlock back to the old value, E2. So that's roughly speaking how this works. So suppose we do one of these DCSSs and the DCS finishes. Can we just free the descriptor after the DCSS is over? Well, it turns out it's not so easy to free because helpers might still access that descriptor. Suppose someone came along and started to help, and they started to execute the help function. The first thing they do is they read address A1 in the descriptor. They read the A1 field of the descriptor. Now, right before they read that A1 field, they can go to sleep for a long time, and then we free the descriptor, and as soon as we free it, they wake up and access A1. That can cause a segmentation fault, a program crash, or it can even cause data corruption if we've already kind of reclaimed and reallocated that descriptor and used it for something else. So that's bad. We need to do our reclamation properly. So how is this normally done? Well, a lot of algorithms say, well, this is just too hard, so we're going to rely on automatic garbage collection. But of course, we don't always have automatic garbage collection. You don't have it in C or C++, you don't have it in embedded environments. So what do you do in those cases? Oh, I should also mention that modern garbage collection techniques are also not lock-free, so you might want a lock-free way to reclaim memory. In any case, if you don't want to use garbage collection, you basically want to use a lock-free memory reclamation algorithm. And a few of them exist, but they're not super easy to apply either. And regardless of whether you do garbage collection or another lock-free memory reclamation algorithm, you're going to suffer high overhead for reclaiming these things. So there's the overhead of actually allocating a descriptor for every operation, the overhead of running the reclamation algorithm so that you can figure out when it's safe to free the descriptor, and the overhead of actually freeing, actually deallocating the descriptor. And it'd be really nice if we could avoid all of these overheads, by reusing the same descriptors instead of continually allocating and deallocating and so on. So the intuition is that descriptors are only needed for helping. I mean, what makes a lock-free algorithm different from a lock-based one is this helping, and you really have descriptors with contents just so that people can look at them and figure out how to help a given operation. And you only need them for the current ongoing operation for each thread, because once a thread starts a new operation, it allocates a new descriptor in a new operation, the old operation's done. That operation doesn't need help anymore. So the dream is to just reuse one descriptor per thread for the current operation. So towards that dream, let's give a descriptor ADT to capture the use of traditional descriptors by existing lock-free algorithms. So we have 4 operations here. The first one is called create new. It takes a sequence of values as its argument. What it does is it creates a descriptor containing those values and returns a pointer to that descriptor. Next, we have read field. It takes as its arguments a pointer to a descriptor and the name of a field. It reads that field and returns it. We have write field, which is similar, and we have cas field, which will actually perform a cas on a field of a descriptor. Now, write field and cas field, these are things used to change fields in descriptors. So these are really just used to kind of manipulate metadata pertaining to the operation, like status information about what parts of the operation have been done to prevent excess work done by helpers and things like that. So not all algorithms even use these operations. How can we use DCSS with the descriptor ADT? How can we implement DCSS using the descriptor ADT? Well, here's the original help function for DCSS. You'll notice that we do a bunch of reads of descriptor fields, and that's really about it. These cases are not cases on the fields of the descriptor. Like, what you're casing is the actual address A2. In the descriptor, you just have like the address itself. The descriptor points to the address that's being changed by this cas. So this is not even a cas field. We really just need to use read fields here. We replace all the reads with invocations of read field, and that's it. That's how you use the descriptor ADT for this. So once you have this descriptor ADT and you can see that it can be applied to some algorithms, it turns out we can relax the definition of the descriptor ADT slightly to come up with a weak descriptor ADT that admits a much more efficient implementation than the descriptor ADT. So what's the main difference between this and the descriptor ADT? Well, in weak descriptors, old descriptors become invalid. So what does this look like? Thread T allocates a descriptor, and then it starts a new operation and allocates another descriptor. Its previous descriptor becomes invalid. So what does this mean? Well, operations on an invalid descriptor fail. They have no effect, and they return nil, which is just a special value that says, hey, you were accessing an invalid descriptor. And it turns out, if we have an algorithm that uses descriptors, then we might be able to transform it in a very straightforward way to use weak descriptors instead, and in doing so, you can have it take advantage of this much more efficient implementation of descriptors. So what kinds of algorithms can you transform? Well, I have a formal description of this in the paper, but I'll give you just an intuitive description here. The idea is it works for algorithms that first create a descriptor and then invoke the help function on that descriptor, and any read field, write field, or cast field operations that it performs are only performed inside that help function. So this is satisfied by the DCSS that we're working on. How do you actually do this transformation? Well, you modify the help function as follows. After each read field or cast field, these are the operations that return values, we check if it failed. If it failed, we simply stop helping. We just return right away. So that might be a little bit surprising. I'm saying, hey, regardless of how help is written, you should be able to just return immediately. That's kind of surprising. But it can make a little bit more sense, at least. I mean, I have a rigorous discussion of this topic in the paper, but it can make a little bit more sense if you just think for a second about how lock-free algorithms have to be designed. So lock-free algorithms have to be fault-tolerant. Processes can crash at any step in the execution, and yet the algorithm has to keep chugging along. That can't be a serious problem for the algorithm. So sort of intuitively, you can see that the help function has to be designed so that no matter which step of a help function a process crashes and stops responding, the algorithm has to continue to function correctly. So at least that gives some intuitive idea of why this would make sense. So why does this transformation work? Why does it make sense to stop helping if we saw a failed read field or cast field? Well, if you fail a read field or cast field, that means you are accessing an invalid descriptor, and that means the thread created a new descriptor since it created that descriptor. That means it started a new operation, and that means the old operation that you're trying to help has already finished. It doesn't need help anymore, so you can just stop. So how do we implement weak descriptors in a really efficient way? Well, we have a descriptor array with one slot per thread, and here's what the descriptor for thread T looks like. We just take the descriptor for the algorithm we're trying to implement, in this case DCSS, and we slap a version number on it. I'll walk you through roughly how this version number plays a role and how this implementation works. Suppose thread T calls create new. What does create new do? It increments the version number, it changes it from even to odd. Now that it's odd, that means this descriptor is currently being initialized, it's in flux, it's being changed. Don't touch it, don't look at it, because you're not going to get a consistent picture of this descriptor. It's in the middle of being changed, initialized. So no one will look at it while it's odd, and then after it's been initialized by thread T will increment that version number again. Now that it's even, it's fair game. There's an operation that thread T is performing. Here's a descriptor that contains all the contents for that operation. Now, what does create new return? It doesn't return a traditional pointer to this descriptor. I mean, it's pretty easy to find a descriptor if you know, for example, the thread that is running the operation. So thread T, I mean, you can find this descriptor if I just tell you the name T, thread T. We give a little bit more information than that in the pointer. The pointer is the concatenation of the thread name T and the version number 4. So I'm saying what's returned by this create new is version 4 of this descriptor, thread T's descriptor. Now if thread T creates a new descriptor, if it calls create new again, it'll increment the version number from 4 to 5 when it starts initializing, and now that it's been changed from 4 to 5, version 4 of the descriptor is invalid. So any accesses to this descriptor that are, following the pointer T, 4 are going to look at this version and see, hey, it doesn't match. We can't access this, just return nil. And there's a little bit of care to be taken in the write field and cast field operations to make sure that they don't actually change any fields of this descriptor if the version number doesn't match what they expect. And that's discussed in full detail in the paper. So we just showed how to deal with algorithms that perform read field, write field, and cast field only inside help. It turns out that there are some interesting algorithms that invoke read field outside of help that we'd like to be able to support as well. So for example, we have the LLX and SCX primitives that I introduced with Faith Ellen and Eric Rupert a couple of years ago. These are really nice for implementing lock-free trees. And we have a K-compare and swap primitive. There's an implementation by Tim Harris that we looked at in this work that also performs read field outside of help. And the real real challenge in dealing with these kinds of algorithms is when we're dealing with failed read field operations inside help, it's pretty obvious what we have to do. There's no need to help anymore because the operation's over. But if a read field fails outside of help, we know a lot less about the structure of the code and about what's happening in the algorithm. We don't really understand the greater context. So that's the challenge. How do we deal with the read fields that fail outside of help? And so we came up with an extended weak descriptor ADT and an extended weak transformation, full details in the paper. I'm just going to give a high-level description here. So intuitively, this extended weak descriptor ADT is similar to the weak descriptor ADT, but you also have access to a predicate called isOperationFinished. Given a pointer to a descriptor, it says, hey, is the operation that created that descriptor finished, yes or no? And roughly speaking, this supports algorithms in which any read fields that are performed outside of help can be replaced with calls to isOperationFinished. So if an algorithm uses read field outside of help, but it's really just trying to figure out, hey, has this operation already finished or is it currently ongoing, then you can use the extended weak descriptor ADT to implement it very efficiently. And it turns out both LLX and SCX and KCAS use read fields outside of help in exactly this way, so they're both supported. So we can accelerate both of those implementations, and in doing so, we can not only make them more practical, we can also accelerate all of the data structures that have been implemented using them. So let's look at some experiments. Here's our experimental setup. We have a system with 2 sockets, each of which contains an Intel i7 4830V3. Each of these has 12 cores and 24 threads, so 48 threads in total. It's 128 gigs of RAM. It's running a recent version of Ubuntu. We compiled it with this version of GCC, and we use the O3 flag for the maximum level of optimization. And we used a fast, scalable memory allocator, JEmalloc 4.2.1. This was a strict improvement on all of the algorithms in all of the scenarios we considered. So we ran 2 different experiments. The first one was a k-compare and swap experiment. So here we have basically a very large array, and threads repeatedly try to do either a 2-cas, which we see on the left, or a 16-cas, which we see on the right, in this array. To do, for example, a 16-cas, you pick 16 uniform locations in this array, uniformly random locations in this array, and then you use the 16-cas to atomically increment each of those locations by 1. So this is a fairly simple kind of change we're making, and it turns out we can use the simplicity, the sort of simple regular structure of this experiment to compute like a nice checksum at the end where we know exactly what all the cells have to sum up to. So we get kind of like a correctness check for free as well. So we implemented 4 different flavors of this experiment. We have a reuse algorithm where we use our technique to reuse descriptors. This is like an extended weak descriptor implementation. And then we have 3 versions that reclaim and allocate descriptors. So we have Deborah, a fast epoch-based reclamation algorithm, hazard pointers, and the read copy update primitives. And you can see that reusing descriptors can have a really large impact on performance here. Additionally, it can have a large impact on total memory usage. So here we have the peak memory usage used to store descriptors in bytes, and this is a logarithmic scale on the y-axis. So what we're actually seeing is that our reuse version uses almost 1,000 times less memory than the next best option to store descriptors. So we also have this binary search tree experiment where we implemented a binary search tree using LLX and SCX. And here we have a workload where threads do 50% insertions and 50% deletions on 2 different key ranges. So on the left we have a key range of size 100,000, and on the right we have a key range of size 1 million. And we have 4 different algorithms we're studying. We have Deborah/reuse, which uses Deborah to reclaim nodes and reuses descriptors using our technique. We have Deborah, so Deborah is used to reclaim both nodes and descriptors. We have RCU reuse, so RCU for nodes, reusing descriptors, and RCU. And you can see in each case that even if we have to spend some time still reclaiming nodes, using memory reclamation to reclaim nodes in a data structure, you can still actually get an appreciable improvement just using, our reuse technique to reuse descriptors. So we're not getting rid of all memory reclamation, but you still actually get a nice performance improvement. So in conclusion, we introduced weak descriptors, which support a large class of lock-free algorithms. We showed that they can significantly improve performance, and they can drastically improve memory usage in some cases. There's a lot of stuff in the paper that I couldn't really touch on here, so there are formal definitions and proofs for everything. We support some more algorithms than I've led on here, so we support algorithms that use multiple types of descriptors or allocate multiple descriptors of the same type. And we do a lot more experiments, including a full suite of experiments on another machine, a 4-socket AMD machine. So if you're interested in that kind of stuff, I invite you to take a look at the paper. And with that, I'll conclude. That's it for the talk. Thank you very much, and I'll see you next time.